Hello, my name is Michael Guzman, and along with Lazaro Morales and Danny Adames, we shall be presenting a power transmission system design. This presentation shall go over the problem statement, the background on transmission systems and gears, the structural design, and then we shall conclude the presentation. Our problem statement has given us 5 goals to accomplish. The first is to successfully design a transmission capable of transmitting 7 horsepower. The second is to successfully produce a speed reduction of 1500 RPM to 125 RPM. The input and output shafts must be in line and rotate in opposite directions. Also, the system itself must be the smallest volume and weight possible, and it must be able to be used for high precision applications.
Most experts agree that it was around 2600 BC that the first gear devices were introduced. They were used for early and primitive pulley systems. Around the 1st century AD, gears began to evolve into their modern form as metal discs with tooth around the outer surface. Spur gears are the most common form of gear, and they are cylindrical in shape and have teeth around the outer surface. Helical gears are also a very common form of gear and are very similar to spur gears, except that they have a helix angle cut into the teeth. Transmission systems are essential for modern life and are responsible for much of the Industrial Revolution. They drive many machines and appliances that we use daily. The first true transmissions originated in the Middle Ages. They were man or animal powered and drove early mills and water pumps. The next big evolution in transmission design was the advent of variable speed transmissions, which came along with the steam engine at its high power loads. The variable speed allowed it to reduce power loads for the necessary application. The smooth gear shifting was the next evolution, which allowed for use of transmissions in many home appliances and in everyday useful machines such as cars. The standard transmissions for vehicles were introduced in the 1920s. This is an early classic design gear train. It's just an illustration to show you some of the evolution.
The design of the gear train started by considering the requirements of the system, such as the power levels, the input and output speeds. For simplicity, spur gears were designed first and tested. Input and output shafts spin in opposite directions. Therefore, an idler gear must be implemented into the gear train. If the spur gears fail, then helical gears will be considered next. American Gear Manufacturer Association procedure equations are listed here. These equations are used to determine the bending stress and contact stress. With these stresses, you're able to find the factor of safety due to bending and due to contact. This is an example of spur gear. As you can see, the 2 spur gears are mating. The spur gears were chosen from the Boston catalog for this project. The gears were selected to meet the requirements of the system. These were the gears that were selected. As you can see, the first gear has 12 teeth and the last gear has 48 teeth. That is because we are reducing from 1500 to 125 RPMs. Once you select your spur gears, you need to do calculations to determine the pitch line velocity and the angular velocity. With these velocities, you're able to determine your transverse loads and radial loads. This table illustrates the loads that were determined for each gear. Once you determine your loads, the bending and contact stresses were determined using the AGMA equations. Once you determine the bending and contact stresses, you're able to determine your factor of safeties. As you can see in this table, gear 5 failed. The factor of safety for gear 5 due to bending is 0.8, which is not an adequate safety factor. Helical gears were considered next. Helical gears are very similar to spur gears, except that they have a helix angle. This helix, because they have a helix angle, they produce truss loads. Another thing that you have to consider with helical gears is that you have to consider the transverse diametric pitch and the pressure angle. The transverse pressure angles are also taken into account. Using the same AGMA equations that we use for spur gears, you're able to determine your contact and bending stresses. But before you can do that, you first gotta choose your number of teeth, such that we did with spur gears. These are the number of teeth chosen for the helical gears. Like I said before, once you do that, you're able to find your your bending and contact stresses using the AGMA equations. These are the bending and contact stresses found. In spur gears, gear number 5 failed due to bending. As you can see in this one, none of the gears failed. Gear number 5 is stable, has a factor of safety over 1.
The next step in our design is the shaft analysis. Considering that helical gears were chosen, we took into consideration the fact that now the shafts shall be loaded in 3 different dimensions. A full stress analysis was performed on the shafts to ascertain the relationship between the diameters and the resulting factors of safety. Here is the tabulated data showing our final diameters and their factors of safety. As you can see here, as the most critically loaded shaft was the output shaft, as opposed to our initial assumption that the shaft with the 2 gears would be the most critically loaded. Slope and deflection analysis was also performed on the shaft to make sure that they were within reasonable bounds, and tabulated data shows that they were, and that our shafts would not fail because of deflection. Another mode of deflection is the critical speed, which is due to eccentricities in the shafts. The critical speeds were calculated for all of the shafts, and they were also found to be within expected values.
After the selection of the shaft is performed, you have to select bearings for your transmission. The bearings that were selected were taper roller bearings. These bearings were selected because helical gears produce a thrust load. This is the equation used to calculate your C10 value. From your C10 value, you're able to choose your bearings. These were the calculated values for the C10 values. From there, you're able to choose your bearing. As you can see, the bearings that were chosen were well within acceptable ranges from the force.
This is a illustration of our design layout. You see you have your pinion, which drives the idler gear, which reverses direction. It's transmitted through the shaft to the output shaft.
In conclusion, the transmission outputs the required revolutions. The transmission has the smallest possible volume and weight. The used helical gears allow for high precision applications. In order to maintain the given speed, the shaft had to be slightly misaligned, and the transmission was within adequate factors of safety. Thank you, and that is the end of our presentation.